Hello, welcome to ZenView Studios Lab. This is a new video on input impedance measurement and output impedance measurement. Specifically, we'll detail how to do that on my QA400 spectrum analyzer. It's the general measure technique that we'll go over, but I won't go in all the details. There are several ways to do input impedance measurements, and I'll just put a link on some other YouTube videos which are plentiful on the subject, and will give you all the technical background if you need more info. Same for output impedance, we'll go over it. The goal here is really to measure on my specific spectrum analyzer. It's just an occasion to show you how I do it, and the idea behind is for next video to be able to show you how I make probes out of that info, specifically 10-to-1 probes or more, even more attenuation, 100-to-1 maybe probes for the spectrum analyzer that I own. And this is a general way you can, the method can be applied for any instrument that you have, and I'll show you how to do that on old probes, but that's for another video. If you liked the video, please don't forget to subscribe and put a thumbs up. I'll appreciate that. And now on to the technical stuff. So we see the setup right now. I will try to detail a little bit what we see. We have the scope probe, the probe that goes to channel 1 here. We have the spectrum analyzer probe. That's the one that we will try to measure the impedance from. We have a decade box that's in series with the signal generator right here. The signal generator is this one. It's an old-fashioned audio generator. Well, it goes to 2 megs, but mostly for audio purposes. And we have, just as a check, the same signal displayed here. It's 300 millivolt peak to peak right here too. The scope and this scope, the digital and the analog, kind of agree. The analog says about 300 millivolts. More to the point is the fluke, which says 100 millivolt 0.197 or so RMS. That's really what we will base our measure on. And this kind of agrees too, because it shows also 100.2 millivolt RMS. That's the DVM from the scope. So the same measure is displayed on both. And so now what we do is we will add a resistor in series with the signal. The resistor in this case will put, I tried before a little bit, so to save some time. I know that if I put not a 1K but a 9K resistor, I get about 50 millivolts, 150 peak to peak instead of, and you see it goes to 50 millivolts RMS here, 50.4, it's almost half exactly. We can go a little better still by adding, and you see now we're close to what we should be. It's about exactly half of the original signal. I'll go back to the original signal. Okay, it's 0 ohm again, and we're back to 100 millivolts RMS here too. So we know that the impedance that we have to put in series to get exactly half is 9.1 kilo according to what it says. I will remeasure the box and the resistance that's in series with the fluke to make sure what's exactly the resistance that it's reading. In fact, from just that look, if this is exact, it's 9.1 K. That's the input impedance that you have on the spectrum analyzer. You diminish the voltage by half in having the same impedance as the impedance of the unit that under test. That's for the input impedance. Again, 0, and this is the other way around. And we're back to 100 millivolts here. That's the story. And now I'll move a little bit the setup so we can test what's the 9.1 K, what it actually reads in terms of resistance. So as I said, now we're going to measure the box. So I take off the probes from there. And all we've left to do is, that's the 1-to-1 probe that we were taking the impedance from. Okay, so now we'll look at the decade box. So we showed it was at 9.1. That's 9.1. We'll set this to ohm and see what it reads. Voila, so it says 9.0729 K ohm. So it's pretty close to 9 kilo ohm. The 100 ohm is really 70, almost 73 ohms, not 100. So it's 9,73 ohms. That's the input impedance at 1K anyway, with 300 millivolts peak to peak, or 100 millivolt RMS. That's what we measured. So this gives us a very good appreciation of the input impedance. With that number, we're going to be able to figure out what resistor we need to put in series to obtain a 10-to-1 ratio voltage diminution. That's 20 dB, or 100-to-1 ratio. And we'll try that. Here is a little view of the other side, which you couldn't see before, where the spectrum analyzers run. And you see right there, I'll give a capture, the signal from that old-fashioned audio signal generator set at 1K. Okay, so now we're going to see, verify, let's put it this way, which resistance we need to put in series to get 20 dB attenuation. That's by 10 voltage wise. We have a little trick we can do here. The generator has a -20. So if you do this, you see it displays 89.7, so it's quite close. Millivolts RMS here, as opposed to about 900 millivolts. So that's really about 10 times. So this is what we ought to get with the resistance we had. So we had 9K. So the first trial would be to add 90K to see what goes on. Well, you see, it's a bit too much. So actually, when we have that, we know that it's probably less. You see, 92, it should be 90. So we're going to add some more resistance. Sorry, the wrong way. And there we're pretty good. In fact, we can go a little further. 1989, voila. It's almost 90, 89 millivolts. It's not so bad. We could go the other way around to see if we can improve. Voila, that's 92.3, or 82.3, I'm sorry. And 82.2. As far as the box goes, if we'll check the exact resistance of this, but 82.2 gives you exactly 10 times, which is 10 times the voltage, which is 20 dB, same as my pushing the button here. So we read 822 here. So we go back to 0. Sorry, the wrong way. Sometimes it's with the decade box. Okay, and we're back to 900. And by the way, this and this agrees, it's 900. And the sure thing is that you can't see it, but I'll make a capture. On the spectrum analyzer, we get the same 900 millivolts displayed with the peak at 1K. So that's reassuring. It's reading the same. And when we get to the 83, we can do it again. 83 here. And it was 2, in fact. 82.2. So we're close to it. And here on the spectrum analyzer, I'll show you, I'll make a capture of it. It's 91 millivolts and show you the capture afterwards. Voila. So to resume, we have now about 20 dB attenuation with that. That means that if we figure out this exact resistance, we add that to the probe, we'll have a 20 dB attenuation. If we want to go to 100, well, we just have to go 1 decimal further. We'll try that now. So I shorten up a bit the search. Here is the result, 9 millivolts, and that's 899K as far as the dial is concerned here. And we'll check those two resistance. And this is a 100-to-1 ratio. Remember, we were at 900 millivolts. We're now at 9 millivolts. And we'll check that again with the exact, to find out the exact resistance so we can actually create our probes. So now we're measuring the actual box impedance. What says 899 reads actually 901K and 460 ohms. So that's for the 100x probe divided by so that the one which will divide by 100 the voltage. And as far as the results we had for the 10x, we had, so we'll set this back to 0. It was 822 here. Voila. So actually for the 10x we had 81.941K. That's the resistance, the actual resistance that we measured. Well, there might be some measurement errors. This gives you an idea how precise you can get to 10x or 100x. I figure the 100x is probably closer to reality because it has a lot more resolution. But this is interesting. So this is the true value that we have, and now it's going to be building time with this probe that I dismantled to put some resistors in it and have a 10x and a 100x probe instead of 1 and 10, which was for a 10 mega ohm input scope. Here is the shot from the spectrum analyzer. You can see the peak is 91 millivolt. That's times 10. If you record, we had 900 millivolts, and it's showing 91, so divided by 10. Here we see the second capture, which is the divided by 100, and you see 9 millivolt for the same 900 millivolts. So that's the probe, will be probe in the time 100 mode. And it confirms that we have the proper values. Hello again. Hope you enjoyed the video. Don't forget to subscribe and push on the like button if you did. Hope to see you soon on the channel, and thank you for watching.